Okay, hello guys. It's a pleasure to finally do the presentation in person and see some of you. And today I'm gonna do these three papers about session-based recommendation with graph neural networks. I want to do this topic because it's kind of related to my intern project. And to start with, I want to do a little background first. So we all had this, I believe we all had the experience shopping online, like Amazon. And when we do shopping, we usually have some targets in mind that we usually click several items before we finally decide which items to purchase. And we call this sequence of actions a session. And in different sessions, people's interests are different. So previously, many recommender systems rely on user profiles to do recommendation, but in practice, it might be unavailable due to some privacy issue. And therefore, recommending items solely based on previously visited items in the current session is very useful for online shopping platform. So to formally define this problem, let V be the set of all unique items in all the sessions. And an anonymous session sequence S can be represented as a list of items, and they are ordered by the timestamp. They just means the items clicked by the users. And the goal of the session-based recommendation is to predict the next clicked item, i.e. Vsn+1 for the session S. And typically, we will predict probabilities y hat for all the possible items. And then the item with top K values in y hat will be the candidates for recommendation. Yeah, so before we move on, any questions about the problem definition?
How to decide a session?
Yeah, so that's usually determined, like in Amazon, we know they divide a session based on time, or like, the browser has some cookies. So once they click close the browser, this session ends. And if this browser is always on, then the session keeps going on. Sometimes the session will end with action like purchase and add to cart. So at least that's what they do in Amazon. But maybe in some other online shopping platforms, they have different methods. Yeah, but in public available datasets, this session is already partitioned, so we don't have to worry about that. And right now, GNN methods are very popular for session-based recommendation, but previously there are of course many non-GNN solutions. Like the conventional methods are like Markov chains and KNN, but Markov chains they combine the past components independently, but such independent assumption is too strong in practice. And the KNN methods actually can be a very strong baselines, and have even competitive performance with the SOTA deep learning methods. And before GNN, RNN-based methods are also popular, but these methods tend to overlook the complex transitions among these items. Also, the unidirectional assumption is too strong because unlike natural language, where order of words are very important, in the session, people can go back and forth, so the order is not that strong. So we will talk about three GNN papers: SRGNN, GCE-GNN, and DHCN. And actually, I think the first paper, our student Yan Qiao is on the co-author. Yeah, so if you can correct me if I have made any confusions or. So yeah, so this one is published on AAAI in 2019, the earliest paper to do session recommendation with GNN. So this paper represents each session as a graph, and in a session graph, each node represents an item clicked in the session, and each edge VSI-1, VSI, means user immediately click VSI after VSI-1. And for each edge, it has an outgoing weight and an ingoing weight. And the outgoing weight of an edge is its occurrence divided by the out degree of its starting node. So like for like edge VE, V2, the outgoing weight you can see is 1 because its out degree is 1 and divided by the occurrence 1 is still 1. And if we see the ingoing weight of V1, V2 is actually 0.5 because there are like 2 edges coming into V2. So it's divided by 2 is 0.5.
So a question, so for each session, naturally it's a sequence. Right? So
Yeah.
why do we have a graph here? For example, from V2, it goes to both V3 and V4, but then
I think it means this represents that when we click V2, there are 2 possible transitions. We might transition to V4 or we might transition to V3. So it's kind of ignore the specific order of sequence, but they want to capture the transition relationship between 2 items.
the observation is sequence, but this graph is not a representation graph for that space position, like for the like underlying transition.
Yes, and actually I believe there can be multiple different sections, all be represented by the same graph.
Actually, we generate one graph corresponding to one section. And so we explain in the paper that we are going to model the complex relationship with the items, right? So they're actually what are complex relationships? Just the 2 and 4 relationships. You here from the figure 2 you see that we have V2 and we go to V3 and we go back to V3. That's very common in scientific representation because you sometimes make repeated pictures. That's why we want to make it as a model as a graph.
Okay, but during this it transferred the sequence data into graph data, so then there's some information loss. In this case, you still know that okay, this only one sequence that is possible, which is go from V1 to V2, then V3, then back to V2, then V4. But it's possible, just assume like we add another item V5 to V2. Then you don't know like whether I go to V4 first or V5 first, or do you keep all this like temporal information, and then there's no ambiguity?
I think there is kind of information loss, but maybe this kind of loss does not that impact the performance, because we compared there are a lot of sequence-based analysis, and you'll find that this kind of graph are greatly out of the mistake.
Okay. Well, what's the advantage or strength that we represent the sequence in the graph?
Yeah, I think with the motivation of this kind of model design is to model sequences as well, to model the relationships among different items, the item relationships. Yeah, just like because in our case we have kind of in our data sets we find out there are so many repeated pages, and in for example in sequence-based methods we actually kind of tended to because during back to 2019 there are not so many transformer-based methods. Most of the methods are RNN based, so actually they tend to only recognize for a certain kind of certain time period of items. So you model it as a graph, so you can explicitly represent the different transitions between items. And with the graph network model, you can remember more long-term relationships.
How I can provide an analogy, right? So in NLP, some people recently also try to see whether the additional structure, for example, the syntax tree, right? So if we add the syntax tree to this sequence representation of the natural language, whether the performance will be better. As you point out, right, if we represent that in the graph perspective, then somehow you can bring in this very far away
Yeah.
nodes together.
Yeah.
Okay, closer.
This kind of, yeah, but actually, this is a very first work in our group. Yeah. In this case, we only deal with very short sequences. So actually, this kind of repeated behavior is not that significant. But later we do a personalized recommendation system that involves multiple users. In this case, all the sessions are anonymous, right? We don't have user recommendations. So later on, we have access to user historical interactions with the recommendation system. We can build a very long user sequences. And during one user sequences, you can have a very big graph that kind of that can represent this kind of complex representations. Yeah, this is the very first work.
Yeah.
That background.
So then for this very first work, I think the main message we'll want to deliver is try to understand why.
Yeah.
Why graph representation sometimes is better than the code representation.
I agree.
So according to my understanding, the advantage of graph-based method is more significant when you sequence it. That's
Yeah, and it involves the repeated statistics to and fro.
okay. So in this case, do you consider the accuracy?
Yeah, actually, you can see the right hand side of the two. You see, we calculate the degree of the image.
So that's degree, but you didn't consider things like multi-graph. So for example, so we have a loop from 2 to 3. So if I do it like 3 times, like 2, 2, 2, 2, 2, 2. When you convert it into a graph.
Yeah, that's right. We actually calculate the occurrence of the fleet, rather than just the fleet. I mean, this figure too only was a very simple. But actually, we are counting the occurrence rather than just one is.
Okay, so did you represent that as multiple axes or?
Not multiple, we just we take the occurrence into account. Yeah, as the weights. So actually, the add is weighted.
Yeah, so actually says is the weight is occurrence divided by the degree.
Oh,
Yeah, and by the way, I think in session recommendation, the length of the session is actually less than 10 in most of the data sets. So just some additional information. Okay, and once they represent the session into graphs, they just the input feature of each node will be the embedding for each item. So different items will have different embeddings, kind of like vocabulary embeddings. And then he will use the gated graph neural networks to get a session level item embedding for each item in the session. And yeah, the right figure shows all the formula for the gated graph neural networks, but it's basically a GRU unit. And I think most of us are familiar with that. And if you're not, you can just look at the figure. So I'm gonna skip the details. So basically, it just use the GNN to get the session level item embeddings. And after that, they generate the session embeddings by combining the long-term preference and the current interest of the session. The current interest of the session are reflected by the last clicked items. So the local embedding SL is equal to the item embedding of the last clicked item. And then the, oh, yeah, okay. This one, yeah. So this is the local embeddings SL equals to the last item in, and the global embedding is computed by aggregating all the node vectors with attention mechanism. So here alpha I is the attention score, Q and W1, W2, and C are all the learnable parameters. Once they have the attention score, they just do the weighted sum to get the global embedding SG, and they will concatenate the SL and SG and do a linear transformation to get the final session embedding.
Can you explain the alpha I?
It's the attention score for item VI. So,
Okay,
so it's,
and what's the, if you is limitable weight,
yeah.
then what's the, what's inside sigma?
So sigma is this, I think it's the same way function.
Okay,
And
inside it.
W1 and W2 are both learnable parameters. Vn is actually the last clicked item. So it represents the current interests according to this paper. And plus VI is the ith item's session level embedding. And C, I think is another learnable parameters.
Yeah. And that sounds real weird. Can you try to explain the inclusion behind that?
Means that, for one sentence, there are two multiple factors that impact the final position. One factor is the current interest, but this is usually the last item. Because what will impact your next action depends on your current action, right? So this is we call it current interest because we don't have a so-called user impact here, so that's also some kind of wording. And another thing is that before you take that next action, what you have done before. So we take a policy, of course, to model the method through an attention network, right? This is to capture the users that's or the sanctions interest before the next slide. So we just use an attention network to model the so to take every item beforehand into consideration.
Okay, somehow you say, when we try to calculate the attention, we want to utilize the last item, using transformation, and also the item itself using transformation. Yeah. And add them together plus some bias. Yeah.
And is this Q the same for each item? Or
No, actually, Q is for every so every section shares the same field.
and every section shall the same W1.
W1 and W2 and W2. Yeah, that's right.
And then if we subtract this Vn, then everyone still
Sorry.
like, I mean, what if we subtract this Vn part from each of the alpha? Because then that sounds to me like a kind of a scalar to each.
I think it's possible, but you have the nonlinear, right?
Oh,
So
yeah.
you have to use the signal to find the outside. Yeah.
And also in terms of the model, what is the T? The epoch number or the layer number or the length of the session? I mean, in T in the previous.
Oh, yeah, T is actually it's the number of
Layer,
the
right?
number of layers. The graph
Oh.
looks in the layer.
So I think this attention mechanism actually puts a lot of weight on the last click items. So it's basically saying the last click item is very important to predict the next click items. Actually, in the later papers, some people try to change this assumption. So we'll see that later. And
Yeah, I just want to make a comment, like how to design attention is very important. So earlier in Yunxin's paper, the GNN paper, actually we tried to just look at the average of all the nodes embedding of the the template, and then try to calculate the attention.
Yeah.
Okay, so this is we want to find a template for every node.
yeah,
Actually, I think we did a study on the model variance. We take the average of the, I think the techniques for extent.
Because the last item is very important because of the intention of the session.
Yeah.
yeah. Also, I think it's kind of because in this session graph representation is actually kind of lose all the order information. So based on this graph, you can now say which item is the first to click and which one is the last to click. So that's why they kind of need to explicitly add the last click item to show its importance. And once they have the session embedding, they just do the inner product with the item embedding to get a score and do the softmax to turn the scores into probabilities. And so once they have the probabilities, they use the cross entropy loss to do documentation. And by the way, when you do the cross entropy loss, do you use negative sampling to like make things more?
Yeah, as I said before, because the length of the extension is relatively short, right? Yeah, we don't need to do the sampling.
But it might have lots of items. Like the vocabulary size could be very huge.
Oh, yeah. I think this is one thing I realized. I didn't do experiments on this.
Okay, so they just do the cross entropy loss.
What do you try to predict in the math item?
But yeah, the next clicked item.
Always next,
Yeah,
next one, not the intentional.
no, it's just the
We
next.
don't have the intention of the whole thing. So actually, we're doing a kind of auto-regression manner evaluation. If we're time t would be evaluated given time 1 to time t minus 1.
In the encoder state, we already incorporate those information. Do you think there's some information leak?
Oh,
No, I think
no. Actually, we, for example, we generate the sensor in an auto-regressive manner. For example, we call, for example, at time on t, we call it ascension to t. Time comes in 1, 2, 3 until t minus 1, and we construct the essential block. And for comes in t plus 1, and we construct the essential block based on what comes in 1 comes in t. Yeah.
For one session, actually, you have this partial block.
Yeah, that's right. So I still not, so if I don't think there's information.
yeah. So to sum up, the SRGN is from the early paper. We use GNN for session recommendation. It uses GG gated graph neural networks and attention mechanism to generate session embeddings, and use cross entropy loss to optimize the model. And I'm gonna skip the experiments part of SRGN because first it's kind of early, and then it actually compared by the other two methods. So we can just see the SRGN's performance in their experiments. So yeah, I'm gonna move to the second paper. Its full name is Global Context Enhanced Graph Neural Networks for Session-Based Recommendation. So according to this paper, SRGN heavily rely on the relevance of the last item to use the user performance preference of the current session. And previous studies only consider the current session while ignoring the useful item transition patterns from the other sessions. Therefore, they propose a novel approach to exploit the item transition over all sessions explicitly. So in this method, they actually have two kinds of graph, the session graph and the global graph. And the session graph is basically the same to the graph in SRGN, except that they add a self loop for each item. And there are like 4 types of edges: in edge, out edge, in, out edge, and self edge. So, and for the global graph tries to capture the transition relationship among all the sessions. So it's a global view. So similarly, each node represents an item, and there's an edge VI VJ if there exists a session S where SI prime and VSJ prime belongs to SS, and VI equals to VI. So yeah, basically it's saying that there exists a session where VI and VJ positions are small. The positions are very close, smaller than threshold sigma epsilon, and this epsilon is a hyperparameter. So like in this example, the epsilon is 2, and if we try to see which node this V2 connect to is basically all the items that, the position difference to the V2 is less smaller or equal to 2. So V1, V3, and V6, V5, V7, V8. So basically, the global graph captures if there's an edge in the global graph, it means Vi and Vj are, likely to be clicked together. And the weight of an edge is its frequency over all the sessions. And to avoid the graph being too dense for each items, only top n edges are kept.
Yeah, but here I have a comment that kind of have a deeper understanding why graphs are. I think we can do the analogy between this deep work, which is like a node embedding model on graph. Essentially, the underlying structure is like between items, as I mentioned, there's some like relationships, maybe similarity or something like condition probability. But what we can observe is what those works. So each session is kind of random work. That's what we have observed. So somehow we want to reconstruct the graph based on the work that we have.
Yeah.
So that definitely will give us like a bigger picture of what's going on. But if we just focus on one session, consider them as sequence, that is just a very small view. So we don't really have that big picture.
Yeah. Okay, so that's global graph. And here's the overview of these entire methods. So given a session, given all the training sessions, we'll construct one global graph. And for each session, we'll construct its own session graph. And then for the global graph, we'll get a global level item representation. And for each session, we'll get a session level item representation. And these two representations are added together, and plus a positional encoding to distinguish the order of each session. And then they will get the final item representation, and then they will use the attention mechanisms to get the session embedding, and then basically do the same thing as in SRGNN to do the cross-entropy loss optimization. So then this is the overview. We're gonna look at each part in detail. First is the global level item representation, which is basically this part. We have one global graph, and each item, same as in SRGN, is in the node feature is just the kind of like a vocabulary embedding. And then they will do use just like GNN to do the message passing thing. So first order, so for each node VI, it's sum all its neighbors information. And here pi is kind of like the attention. And the pi is the attention score between Vi and Vj. And it's calculated in this equation. Q here is the representation, is a learnable parameters. And I think L is the layer, it is the layer number. Also W is also the layer number. And here, HVJ is the current input embeddings for Vj, and Wij is the weight. Yeah, I think it's the weight for between Wij. And here S can be seen as the features of the current sessions, and it's defined as the mean of all the V in the sessions, all the atom embeddings. And so pi is then normalized with softmax function. Then, so this is to update the neighbor information. And then the HVG is updated by this formula. It's the ReLU of the W2 is another learned parameters with HV and H neighbors embeddings concatenated together. And then the final item layer is just to aggregate the message of the previous layer and its neighbors things together to get this one. Yeah. So it's a GNN and it designs all own message passing framework, but it's basically just GNN. Yeah, so that's for global level item representation. And then we're going to look at the session level item representation, which is this part in the overall method. So for each session graph, it will get just another session level item representation. And it's basically still just a message passing framework. And here the alpha ij is the attention score and is defined in this way. Here Rij is actually the learnable parameters, and actually Rij is the relationship between the edge tag between V and Vj. So it can be in, out, and self. And for different edge types, it has its own learnable parameters. Yeah, so once they have both the global level item representation and session level representations, so the final item representation is the summation of these two. So let H be the final item representations. They will use a learnable position embedding matrix P and to distinguish the order of all the items. And H and P are combined by this formula. And you can notice in this formula, P is actually reversed. And it is reversed because similar to the idea in SRGN, the last clicked items is the most important one in the session. So if it is reversed, then the last clicked item is always combined with P0. And if it's not reversed, then actually the last clicked item will be combined with different position embeddings, which is actually bad for prediction. So that's why the position encoding is reversed. And then the session representation is computed by another attention mechanism. Here, beta is the attention score. It's computed here. And again, here it has an S prime. It's basically the mean of all the final item representation. So it has the S prime as a coarse representation, and use this coarse representations to get the attention score for each item, and then just do the weighted sum.
Just to understand in this way, so there are two attention mechanisms, but the first attention is like more like a graph attention network.
Yeah.
The second attention is try to do this, try to get this graph level representation.
Yeah. And then the prediction layer is basically the same as in SRGN. So yeah, so I think compared to SRGN, these methods have two kinds of improvements. First, it adds this global graph to capture the global transition relationship instead of only the transition relationship in the current session. And second, it adds this positional encoding. And I think that's thanks to this positional encoding so in the SRGN, the final session embedding needs to emphasize the last click items, but then this one, because it can tell which one is actually the last click items, so its attention mechanism doesn't have to emphasize which one is the last one. Yeah, and for experiments, if you use 3 data sets, Diginetica, Tmall, and Now Playing, so you can see that all the average length of each session is smaller than 10. And the right one is all the baseline it compares to. The SRGN is here, and there are other RNN-based methods and GNN-based methods. And the main evaluation metrics are precision at 20 and MRR at 30. P at 20 is represents a portion of correctly recommended items amongst the top 20 items. And the MRR is basically, this formula is here. So it's like the average of the rank position of the first relevance of the first. Yeah, so it's the rank of the correct items in your prediction. And here are the results. So among all the baseline, you can see that SRGNN is actually perform very good. So SRGNN is indeed a very strong baseline in this paper. And GCE actually beats all the baselines. And you also do some ablation studies, like the GCE GNP is the with forward positional encoding. It means like in this, it's actually changed this part. So it's not positional encoding is not reversed anymore. It's just forward one. And the essays use just ignore the position aware attention, just to ignore the position encoding. And the ablation study shows that these two actually quite important to the performance. Yeah, and then we're gonna look at the last paper, self-supervised hypergraph convolutional networks for session-based recommendation. So, according to this paper, GNN-based methods regard item positions as pairwise relationships, but it ignores the complex high-order information among items. And he argues that hypergraph provides a natural way to capture beyond pairwise relationships. And then to overcome data sparsity, they introduce a line graph channel and integrate self-supervised learning to help train a better model. So I'm going to provide two definitions that's kind of important to this paper. First is hypergraph. So like G equals VE denotes a hypergraph. The V is the same as which is the set containing all the I vertices. And the difference between hypergraph and graph is that E actually can connect two or more vertices. So, and it is assigned a position weight, and all the weights formulate a diagonal matrix W. The hypergraph can be represented by an incidence matrix H, R n times M. N is the number of vertices, and M is the number of edges. And basically, H I epsilon equals to 1 if the hyper edge epsilon contains a vertex VR, otherwise it's 0. And for each vertex and hyper edge, their degree are represented in this way. And then the line graph of hypergraph is, so the line graph, the node in the line graph is the edge, represents the edge of the hypergraph. And two nodes of the line graph are connected if their corresponding hyperedges in G share at least one common node. And we can actually see an example of the hypergraph and line graph here. So assume we have three sessions. Session 1 contains V1, V2, V3. So this session is basically a hyperedge in the hypergraph. It's this one, E1. It contains 3 vertices, V1, V2, and V3. And S2 contains V2, V4, V5. So it's this edge. And S3 contains 4 vertices, and it's this edge. So that's the hypergraph constructed by these 3 sessions. And you can actually connect so like each hyper edge can be represented by a complete graph. So it's actually can be transformed into this way. And the line graph, so E2 is the edge of E2, and E1 is the hyper edge E1. And E1 and E2 is connected because they share the same node V2. And similarly, E2 and E3 are connected because they share the same node with V5. And similarly, E1 and E3 are connected because they share the same node with 3. So that's the hypergraph and the line graph of the hypergraph.
I always have this question, whether this hypergraph is really necessary. But here they try to use hyper edge to connect to different nodes. Right? But we could have another way to construct graph reading a pseudonode. The pseudonode is just this hyperakt. But I just don't know, like, whether all the methods defined on this radiograph, because now we turn this hypergraph into radiograph. So whether everything works on the radiograph could work on the study. Just think about this, right? So consider this research network where we have papers. The actual paper is kind of hyper because they connect to like authors and the venue and the keywords. But it would just treat those papers as application notes. And then we can just apply regular methods to it. I always have this doubts whether this hypergraph is necessary. I know like lots of people try to pay special attention to hypergraph.
Yeah, that's a good question. And so like in this case, if we have a pseudonode represent each session, and then each vertex connects to the session if it is belong to this one.
Mhm. You probably can think offline if you
Yeah.
don't have the answer.
Yeah.
But I always have this question.
Yeah, and I also have a question. It looks to me that you construct each session into a hyper edge in hypergraph. And then each hyper edge is essentially a complete graph of all the past items.
Yeah.
So in that case, the sequential relationship is from the order and the connectivity of the original session is broken.
Yes, it's actually broken, and I believe the recover this information by adding the additional encoding same to the previous paper. And at least I think I'm not sure adding the pseudonode if they can achieve the same thing as hypergraph, but at least compared to this hypergraph representation between the previous graph representation, I think the advantage of this hypergraph representation is that it's so like if there are three things often appear together, then hypergraph provide a better representation for this kind of relationship, because the edge in graph can only do pairwise relations.
I also think there might be like less focus on the kind of sequential kind of thing, not like in the previous formulation. If A, then B, then C, versus the A, C, D, that's the different one. But here they are the same.
Yeah.
So they even further diluted the sequence information.
Yeah,
That's something that I have to think about.
It only doesn't mention the solution.
Yeah, but like since that they separated two, because that previously the ACD and ABC are two different ones. Right? Yeah, clearly.
But if you add the solution photo, so we turn the template, but we still have the template information. So when those items have been clicked, we still have some information. So that will be converted into a solution photo. So that will be the actual feature of the node. So the all the information can be recovered from the solution photo. Do you think that was sort of the concern?
Yeah, I mean, actually, what I'm trying to say is that maybe the previous kind of formulation, the difference between ACD and ABC might cause some kind of confusion, which is, something that we need to be separate in, for example, position coding in this work. Yeah.
So right now we still have the computer, we still need to have the position.
Yeah. Yeah, we can talk about this.
Okay. And so here's the overview of this DHCN method. Once again, it represents all the sessions into a hypergraph. And then they will also create a line graph from the hypergraph. And then it will, given the initial item embeddings as input features, they will get one session embeddings based on the hypergraph and another session embedding based on the line graph. Then they will do a self-supervised learning between two different session embeddings. And by the way, this is just contrastive learning. They try to distinguish if two embeddings represent the same session. And so this is one helper learning task. And then the main task is still predict the next click items using the cross-entropy loss. So let's look at the hypergraph convolutional networks. Similar to the GNN, the node reputation is updated by aggregating its neighbors. So for node I, it's updated by basically it's W. I think W is the weight, and it's basically summing all the neighbors. So the neighbors means all the things that connect to the by hyper edge. Yeah, and it seems and it doesn't have any non-linearity. I think I remember especially mentioned in papers, they kind of try to they don't use any non-linear function, they just do this aggregation. And it can be written, so this one thing can. Yeah, so let's understand this equation. So W sigma is the weight of the edge between I and J. And here HI sigma and HJ sigmas are both one. So H can be 1 or 0, and they need both to be 1 to be summed into this thing. And they are both to be 1 only if they appear in the same hyper edge. So again, epsilon is the index of the edge, and HI epsilon is 1 if and only if item I is in the hyper edge epsilon. And also HJ epsilon is 1 only if item J is in the edge epsilon. And then if they are both in the edge epsilon, then this thing is just the weight of edge epsilon. Then it times the embedding of xj. So that's how they aggregate these neighbors. And it can be written in matrix form with row normalization, which is like this. And the final node representation is the average of node representation of each layer. Then the positional embeddings are added into item rotation in the same way as in GNN. And the session embedding is actually obtained in the same way as in SRGN. So that's how they get the session embeddings, this session embeddings. So basically, once they get, it's kind of like, I think they get the item embeddings from this one global hypergraph. And then for each session, it uses these attention mechanisms to get this own session embeddings. And then we're gonna look at how they do the self-supervised learning. So we know that they have the line graph, and the line graph, the node in each line graph represents a session. And each two nodes are connected if these two sessions share the same items. So the edge actually kind of represents the similarity between sessions. So the line graph can be seen as a symbol graph, which contains the cross-session information and depicts the connectivity of hyper edges. So each node in the line graph represents a session. The input features are the average of the item embeddings in the session. And then you use GNN to get the embedding of each node. The embedding of each node in the line graph is the embedding of the session. And then you try to maximize the mutual information between the hypergraph representations and the line graph representations. So that's what the self-supervised learning task to do. And for each mini batch, including n sessions, there is a bijective mapping between the two groups of session embeddings. The goal can be seen as to distinguish
which two embeddings represent the same session. The loss function is here. The FD, the negative sampling are obtained by row-wise and column-wise shuffling matrices, Fisher matrices. And FD is basically a distinguish function. It can be just a dot product. And the overall loss function is LR. LR is the recommendation loss, and LS is self-supervised learning loss. And the experiments here, you can see the method has DHCN and S squared DHCN. S squared DHCN represents the DHCN with self-supervised learning. So, and it doesn't compare with the previous GCE GNN, but it does compare with SRGN. And actually outperforms all the baselines. Yeah, and you can actually see that by adding the self-supervised learning actually help improve the performance of DHCN. And here are some observation studies. The first one exclude the positional encodings, and the second one exclude the self-attention mechanism. And you can actually see the results. Yeah, and interestingly, in TMO, some of the by removing this thing actually improve the results. So, yes, well, that's the application. What the application studies say. And here's the impact of beta. Beta is here, the loss function. And basically, adding the beta slightly improve the performance when beta is not too large. If the beta is too large, the performance will degrade. Yeah, that's all I have for today's presentation. Here's the full reference for the 3 papers. Any questions?
Thank you, David. I have a question. I think I raised earlier. So, how do you design the experiments? Because the encoder also utilizes the session information, and decoder also uses the session information to form the upper function. So how do they separate to avoid the information?
So I think for the first 2 papers, in the training session, here, let me see, in the problem definition, we can see that like in SRGN, because it doesn't have a global graph. Yeah, but they just don't encode the entire session. And for the last 2 papers, they had this global graphs. And I think they just don't include the test sessions in the training stage.
So the loss will, you mean that when we formalize the loss function, those links actually have been seen in the encoding stage.
Yeah, it might be seen in the global graph, but in the session graph, it won't be included. And I think in global graph, this leak is fine because the global graph will be very big. So
in that case, kind of just try to fix the data. It's kind of reconstruction. Yeah, so the reason I mentioned reconstruction loss, right? Suppose we have an encoder completely in this graph, and then we try to utilize the embedding to reconstruct the graph, and then try to compare the decoded graph and the input graph. So definitely the information loss, but still with that, we can train a very nice encoder. So here, I think your we try to say that doesn't matter in the loss function that we have included that have been seen earlier. Because it's not about text, it's just about try to formalize a function to do the training. Is that what you can say?
Yeah, kind of. So yeah, so like in this GCE gene, I think your concern is like the next click items might be already be seen.
Mhm.
But so like given a session, it will not be seen in the session graph because the session graph will only contain the previous click items. It might be seen in the global graph. But I think the global graph will be very dense. So it actually connects to many like end edges. So
It's an aggregation. Even your node aggregation doesn't mean that you know this specific section.
yeah,
Still, you should be very careful. To do the encoding.
yeah. And similarly, I think for the hypergraph, once it also is still same issue. It has the like a global hypergraph, but still you need to distinguish for each session, specific session to do that. So
And then for the test, because they completely put some sessions into the test, so they will not be seen in the training stage.
yes,
So then they have an issue.
yeah. And by the way, they so in practice there might be some items in the test set not seen in the training set, but actually in the experiments they just ignore all those items.
I think that it can be easily solved if we incorporate some features of those items.
Yeah, but the data sets they use, they don't have any.
Just IDs.
Yeah, just have. Yeah, any other questions? Or maybe from the Zoom?
I have a question about the hypergraph computation. So in the framework, we already transferred the hypergraph to like a web and
Did what?
So I wonder like, how necessary it is to use that HP channel instead of standard of this platform.
Yeah, actually, I think it's kind of misleading using this transform hypergraph because I don't think their paper I don't think they explicitly transform the hypergraph into this way. I'm not sure why they draw things like that. Yeah, perhaps just for illustration.
So their graph is represented as a hypergraph. It's not represented as this.
Yeah, they use this incidence matrix to represent the
What
hypergraph.
is different in the later formula?
Yeah, here. H. So I think this one is just for illustration purpose.
Yeah, for this one, I still have that question, whether it's hypergraph or is necessary.
Actually, I looked at their like numbers, like the 13 to 7 on the second.
I think they use, yeah, we can try to compare that because they use the same data sets. So let's see, this one is 22. I don't know, is there a better way to compare this? Let's see, let's move the slides together. Hey, actually, it, yeah, you can see it's not, no, it's not in the same order, but let me see if we have.
It's difficult. How can I do this right? Maybe I can just wait. Let me just copy it here. Yeah, we just like for Diginetica, this one is 40, and this one is 41. For Timo is 28. Is 26. It's not playing is 16. This one is 17. Yeah, so indeed, this hypergraph methods does not outperform the GCE methods.
Which one was published earlier? Where were they published? I think only for the first paper.
Yeah,
was the-
Actually, the second paper published in SIGIR 2020, and the last paper published in AAAI 2021. So last paper is actually published later, but it doesn't compare with this second paper. Yeah.
It's like a few months away, then it's difficult. So when you're summing, maybe the first paper hasn't been accepted yet,
Oh, yeah.
because the review process takes quite a long time.
Yeah, probably. But I think the advantage of the third paper is they have this self-supervised learning to try to improve the results. I think it's kind of useful for the domain-specific task, because especially if your training set is small or like have this sparsity issue, then this self-supervised learning actually improve the results as shown in the experiments.
So I'm trying to think about like for the language of using of the graph. So I'm not completely sure this is for the language, but it seems like if we have a hypergraph, hyperhash connecting to units, then basically one layer of like GNN can exchange messages between all units. But if we create a pseudonym, we need like two layers. Right? We need to go through the pseudonym. Then in this case, if we have a more like two hyperhashes, then as long as they share a node, they can share messages in two hops. But creating pseudonodes make that four hops. So just saying that compared to regular graphs, maybe hypergraph has the advantage of helping nodes to share information more requires less.
Yeah.
Yeah, just some of my thoughts. I'm not sure whether this is actual.
Or maybe just hypergraph provides a better abstraction, because maybe in some situation the hyperedge does not only represent a relation. So it's adding a pseudo node just maybe make people difficult to understand. So they use hyperedge.
Yeah, so first of all, I agree with you. But still somehow I just hear it's just a data structure. Just like how to define native.
Yeah.
I remember probably 1 year earlier, just to discuss how to construct the graph structure that with different particular coding, for example, that to avoid the information loss if you converge from sequences to graphs. I think this is the same part of the pricing performance data. It's published in PhD coming from the
It's kind of put pressure.
yeah, but actually it's still defined on a very regular graph, not hypergraphs. But actually we did discuss several ways to construct from sequences to graphs. And I don't think the graphs are that useful actually. And the statement that the sideways of the viewer. There is I think just there is something to do and I'll reject I have no idea why we have years to why we have that.
It seems like people like the hypergraph. So this
This
is
is like the story, maybe.
yes, this year getting back to the portfolio on hypergraph. I haven't read that paper yet, but I mean, yeah, probably hypergraph has some. Like
But it feels to me, even in present, that this matter is complex, but complex doesn't.
yeah, for that I don't.
Yeah, for method passing, right, so if you're saying, for example, if they don't utilize hypergraph, but try to convert it like a hypergraph, in the session. You can say, for the message passing, I do not receive message from my immediate neighbor. Okay, I receive message from my two neighbor. Because if you look at the formula for the hypergraph, when they try to decide neighbors, they still need to have this matrix multiplication, which is longer than because of the X matrix. So if we have a way to decide your neighbors, then we don't have to go with 2 layers, just like the chain definition. It's very similar to the metapath idea. When we do the metapath statement, I'm saying, okay, I don't just do the metapath from a community neighbor, but maybe it's to have a way of to have to with different meaning. So I try to like mathematically how that will increase the example specificity of the document method. Somehow I didn't see that. It's like you present your data in a different way, but the main idea is sort of different.
I see. So it's like for this kind of representation, we use this matrix.
Yeah.
Language, that kind of representation is different matrix.
Yeah.
But it, yeah,
Or because some sort of matrix.
So shall we call it today?
Okay.
Yeah, okay. Yeah, thank you guys for being here.
Thank you very much. Thank you.
this is kind of important.